Hi, physics class. Today, I want to continue going over our projectile practice problems. So projectile motion, if we recall, was when we take an object and the only force acting on it is the force of gravity. Now, projectile motion is an easy motion to understand because oftentimes a lot of the variables are going to fall out of our kinematics equation. For example, there's no acceleration in the x direction. That makes things very easy to find when we're talking about the x direction. In the y direction, typically we'll start with no initial velocity. Though we can start with an initial velocity, that does make the problems harder, and that is not going to be my goal for you guys. I just want you to be able to understand simple projectile motion. So let's do a few more problems. We started this topic last week. Let's keep going on and get a little bit deeper. So what I want you to see today, we got 4 problems, and they're all going to be involving a projectile, and we're going to be launching that projectile at a certain velocity, but we're only going to launch it horizontally. We're not going to have an x or a y component. Like I said, that does make our problem a bit simpler, but I want to get you practicing using the formulas. So in our first problem, a tiger leaps horizontally from a 12-meter high platform with a speed of 4.5 meters per second. How far away from the base of the platform will the tiger land? So before we get started on any of these, what I'd like to do is just go over some of the a quick review of some of our base equations, right? And we talked about this last week, but if we talk about the position of our object, we could start off with our base equation, xf equals x0 plus vx0 delta t. And in the past, there's been another term there that would be a delta t, 1/2 a delta t squared. But we have no acceleration in the x direction when we're talking about projectile motion, so we can drop that term. So our x position is real simple. xf equals x0 plus vx0 delta t. And we're going to do a similar thing with our y position. And here I just plugged in the value of -10 meters per second for our acceleration. That's the acceleration due to gravity. Now, I did leave that vy0 term in here for the moment, but at least for the problems we're going to be doing today, we're always going to have that vy0 being 0, so it'll fall out. And similarly, we could look at the equations for velocity, right? For velocity, and for velocity, we have usually there's an a delta t term in it, but for velocity in the x direction, there's no acceleration, so we have a constant velocity in our x direction. The Vx final is the same as Vx initial. In our y direction, of course, we do have an acceleration. That acceleration is -10 meters per second squared, and just plug that into our formula. So I want to highlight those two because that's going to drive everything we're doing today. We're going to look at these 4 formulas to drive our answers. And really, if you these are all based really off of that one equation, xf equals x0 plus vx0 delta t plus 1/2 at squared. And all we're doing is we made it into 2 directions, 2 dimensions, of an x and a y dimension. And then we also have our velocity equation, vx final is equal to vx naught plus at. Right? So we just applied those 2 equations to a 2-dimensional problem. And this is the 4 formulas we're going to end up with. So let's apply this to our first problem here. So in our first problem, I'm going to write down what are the variables that we have. What is it that we know here? Right. So our problem told us that the tiger leaps horizontally from the platform. It doesn't tell us where the base of that platform is. So we're just going to say it's at 0 meters because it's just asking us how far away from the base. So we can assume that x0 is 0, and we can just go through our calculations to find our xf. Told us the platform was 12 meters high, so there's our y equals 12 meters. Told us that our final position, it hits the ground, so that means yf is 0. And it gave us our initial velocity in the x direction, 4.5 meters per second. And our initial velocity in our y direction is 0 for the day. We're going to be using only ones that have vy0 equals 0. So let's start plugging those in. If we're trying to find how far away, we need our xf equation. We need our xf equation. So we're going to take our xf equation that we have written here in the box up in the top, x0 plus vx0 delta t. So we need to find delta t. We know our x0, we know our vx0, but we don't know our delta t. So how are we going to find it? Typically, you'll find that in problems that we're going to have in our physics class. You can use the one equation, but you don't quite have enough information. So now we got to find out something else. We got to find out delta t in this case. So looking up at the information that we do have, what do we need? What do we know? Well, we know if we want to find our delta t, what else do we know? What can we use? Okay, there's only two other places that our delta t occurs, right? We can look at our velocity for our yf direction, right? But we don't know our initial velocity, nor we know our initial velocity rather for y, but we don't know our final velocity for y. So maybe that's not the best one to use. So let's look at the other one where we have a delta t. Let's look at our position equation over here. We know yf, all right? We know it's 0. We know y0, that's 12 meters. We know velocity and y0 is 0, so this term's actually going to fall out. And finally, we know this last term, negative 5 meters per second squared times delta t squared. So we do know this one. We can get our delta t from this equation. So I'm going to rearrange that y position equation, take advantage that vy0 is equal to 0, and we can just write our equation is delta t, right? Our equation is just simply going to be delta t. And when we rearrange it, we're going to get yf minus y0 over negative 5 meters per second squared. Now, I do want you to be careful. Make sure we have the right signs here. Negative 5 from our acceleration is important. We're then going to plug that in, right? Plug in our yf values and our y0 values. We're going to get negative 12 on the top, negative 5 on the bottom, and then we take our square root of that. We're going to find out it took 1.5 seconds. So the key thing here is if we know certain pieces of information like we did here, we know our initial position, we know our final position, we know our acceleration, we can figure out how long it took to cover that distance. And that's exactly what we needed to find in this sub-step of our problem. Well, now that we know that 1.5 meters per second, let's plug that in to our original equation we were looking at. xf equals x0 plus vx0 delta t. So we know our x0 is 0 meters. We know our vx0 is 4.5 meters per second. The problem gave us that. And we just figured out what our delta t was of 1.5 seconds. So we get an answer of 6.75 meters. So once again, what do I want you to do when you're thinking these problems? Write down the things that you know. Write down the things that you know. Just look at the problem, write down what you know. And be careful, because sometimes it won't explicitly say that. Like it did not explicitly say our x0 is at 0 meters. We could just infer that from the problem. It also doesn't quite explicitly say yf equals 0 meters, but we are talking about the Tiger landing. So we know the Tiger is going to end up at 0 meters. And doesn't really say explicitly that our vy0 is equal to 0. But it does tell us the Tiger leaps horizontally, so it tells us the only velocity he has is in the x direction. Okay, so you might have to read a little bit into the problem, write down the variables that you know, find an equation that best fits. Right, so we know we're looking for xf, so we wanted to use an equation that had xf. Of the equations that we have up here, there's only one that we have, xf equals x0 minus vx0 delta t. But we can't quite use that yet because we don't know what our delta t is. So then we looked at another equation. How else can we get a delta t? Again, there's only two equations that it occurs in. Talked about the velocity one. That equation is not going to help us because we don't know the final velocity of our Tiger. We just know its initial velocity. So let's look at the other one for position that has our delta t. Yep, we know our yf, we know our y0, we know our vy0, we know our acceleration, we know everything we need to know. We can find delta t from that equation, which we did. We found out that was 1.5 seconds. And so once we know that we have our delta t of 1.5 seconds, we can go back to our original equation and just simply plug in that 1.5 seconds for our delta t, and we can find out our final distance, 6.75 meters. You're going to see this pattern over and over again, so I can't stress that enough. Let's look at another one. The Royal Gorge Bridge in Colorado is 321 meters above the Arkansas River. So what if we kick off a rock horizontally off the bridge? The rock lands 45 meters from the base of the bridge. What was the speed of the rock when it left the bridge? So again, I want you to start out. Let's write down, what do we know? What do we know? We know x0 is 0. We kicked it off the edge of the bridge. And we know xf is 45 meters. It told us that it went 45 meters from the base of the bridge. We know y0, 321 meters. And we know yf is 0 meters. It hits the ground. So now let's start looking at our equations. It's asking for the speed of the rock when it left the building. So we know we're going to be going back to one of these. We're going to be going here. We're going to be looking for our velocity of xf. And there's only one place that velocity of xf occurs. It's in this vxf equals vxo. Right? So we want to, how are we going to find our vxo? So we're going to go back in here. If we want to find our velocity that we kicked it, right? We want to find vxo. Do we know xf? Yes. Do we know x0? Yes. But again, we don't know delta t. Again, we don't know delta t. So how are we going to find it? We're going to rearrange our equation. And we see vx0 is equal to our delta x, or xf minus x0 over delta t. We need to find delta t again, just like we did in the top problem. And we're doing the same process we did. Do we know our yf? Do we know our y0? Yes, we do. And we know our acceleration. So we can use this same equation here, this delta t equation. And this time, when we plug in our values of 0 meters and 321 meters, we find out that our time is going to be 8 seconds. 8 seconds. So if we want to go back now, this problem asks us something a little bit differently from the previous problem. We know our time is 8 seconds. We're trying to find our velocity of x0. Let's look at our equation up here. Now we got to plug things into our equation that we had here. All right. So let's plug it in. Vx0 is equal to xf minus x0 over delta t. We knew the 45 meters into 0 meters. We just calculated the delta t being 8 seconds. And we see that our velocity must have been 5.6 meters per second when we kicked this, when our speed must have been 5.6 meters per second when we kicked it off the bridge. Okay. So we're always going to take advantage, often we'll take advantage of this fact of how we're going to find our delta t. Right? If we know how far it's fallen, we can figure out delta t pretty easily. Let's go on to our third of our 4 problems. And this one I'm going to do in steps with you. So you see it has a part A, a part B, and a part C. Try to help you through the thinking process. So again, we're going to start with, what do we have? A diver running at 1.6 meters per second dives out horizontally from the edge of a vertical cliff. Diver hits the water 3 seconds later. Well, what do we know? What do we know here? We know that our x0 is 0 because he's dives from the edge of the cliff. We know our y final is 0 meters, right, because he's hitting the water. What's our initial velocity? 1.6. The problem tells us that because he dives straight out horizontal. If he drives straight out horizontal, that means we have our Vy0 is also equal to 0. And we were told our delta t. So now what are we looking for? We're looking for a yf. We're looking for a yf. So we do have an equation for yf. Do we know enough information to plug into it? Yes, we know our y0. We know our Vy0. Yep. And we know our delta t. So let's just plug in those values. Right. Let's plug in those values, and we see that y0, right? We write down our simple equation equals yf. We have to rearrange it for y0, sorry. So we rearrange our equation for y0. Y0 equals yf plus 5 meters per second squared times delta t squared. We know our yf was 0 because it was at the ground. We know our acceleration. We know our time. We just calculated our time was 3 seconds. And so we put them in together. 5 times 3 squared, 5 times 9 is 45 meters. So our cliff was 45 meters high. Again, so sometimes we just have to rearrange the equation and plug some things in. How far from the base of the cliff did the diver hit the water? Okay, so we're going to be using our xf equation. We know we have no acceleration in the x direction. So our xf equation is really simple. x0 plus vx0 delta t. We know what x0 is, 0 meters. We know what vx0 is, 1.6 meters. We know what delta t is because they told us it was 3. And it looks like I left out my equal sign. This should be 1.6 times meters per second times 3.0 seconds. Should give us 4.8 meters. All right, and finally, what speed and at what angle did the diver hit the water? Well, what I want you to think about here is, what do we know? We're asking for that final velocity. So we want to know the angle and the magnitude of that final velocity. So we need to find Vx and Vyf and theta, right? That's what we're looking for. If we want to know the speed, we need to know the components of our vector. How are we going to do that? Well, the first part is we know that Vxf is equal to Vx0 because we don't have any acceleration. And we were told that our Vx0 was 1.6 meters per second. So our final velocity in the x direction is pretty simple, right? It doesn't change. How about our y direction? How about our y direction? If we look at this equation for our y equation, I just wrote down what we had in the front page. Vy0 equals negative 10 meters per second squared times delta t. Well, we were told that our delta t was 3 seconds, so let's plug that in. And we know that our final velocity in the y direction is negative 30 meters per second. Well, if we know Vxf and we know Vyf, we know the velocity. We can calculate the magnitude of our velocity. That's simply the square root of the sum of the squares, right? Just our old Pythagorean theorem. Let's plug in our values for Vxf and Vyf. 1.6 meters per second squared, negative 30 meters per second squared, and we're going to get out 30.04 meters per second. Right? Not very much. That 1.6 meters a second really did not change the overall velocity very much. It's barely over 30, and it started. And we know that our y component was 30 as well. So you start moving that fast, it's even a little. If your x is very small compared to your y, your answers can be very close to your y. Okay. So we know our velocity. How do we figure out our angle? Well, we know that our angle is equal to the arctangent, right, of our vectors. So our rise vector, our y, divided by our run vector, our x. So let's do that. The inverse tangent. What's our y? Negative 30 meters per second. What's our x? 1.6 meters per second. You plug that into your calculator, it's going to tell you it's negative 87 degrees. Negative 87 degrees. Okay. Good. Let's move on to our next problem. Problem number 4. A ball is thrown vertically from the roof of a building with a speed of 7.2 meters per second. Hits the ground with an angle of negative 75 degrees. What is the height of the building? Now, this one's a little harder. But I want to show you that if you follow our process, you can figure it out pretty easily. So again, I want you to write down, what is it that you know? We know x0 is 0 meters because it's thrown horizontally from the edge of the roof. We know that our y final is 0 meters because it hits the ground. We know what our initial velocity is in the x direction because we were told it was thrown horizontally at 7.2 meters per second. And we know that our velocity in the y direction is 0 because it's thrown horizontally. And finally, we know that our theta is 75. And actually, I'm sorry, guys, I missed that negative sign there. So what are we asking for? We're trying to find our YF. We're trying to find our YF. And here's our equation for YF. What do we know? Yep, we know our Y0, we know our Vy0, but we don't know delta t. So we got to find our delta t. Let's look at the other equations. Do we have anything else that can help us figure out our delta t? We do. We have the equation that says Vyf equals Vy0 minus 10 meters per second delta t. Okay. Well, that only helps us a little bit because we still don't know Vyf. We don't know our final velocity. But this we can figure out. This we can figure out. Right? But what do we know about our final velocity in the y direction? We know that that's related to our angle of 75 degrees here, our negative 75 degrees. We know the angle the ball hits the ground is our tangent of theta is Vyf over Vxf. But we don't have Vxf. Well, wait a minute, really we do. Because we know for a projectile that our Vxf and our Vx0 are the same. Our final velocity in the x direction is equal to the initial velocity in our x direction. So we know our Vxf is 7.2 meters per second squared. Wonderful. We know our VXF, we know our VYF, we know our tangent rather, now our theta, so now we can back into VYF. Let's rearrange our equation, solving it for theta, and what do we get? Our VYF is equal to VXF times the tangent of theta. We were given VXF, we were given the theta, so we calculated our VYF is 26.9 meters per second. Good. Now, I think that was the hard part here, to realize, how do we use this part of our information? How do we use that part of our information? And that's really where it tells us. The tangent of that theta tells us our velocity in the y direction divided by the velocity in the x direction. So we're able to get our VYF. Well, now we can plug it in. Let's plug it into this equation up here. Okay. What does that give us? We rearrange this top equation here. Let me do this in blue instead. Is that going to work? Yeah. Well, it's going to look green when I color over it. We are going to rearrange that equation, and what are you going to get? You're going to get delta t is equal to VYF minus VY0 over 10 meters per second squared. Okay. So let's go ahead and plug those in. Negative 26.9 meters per second, because we just figured that out for our VYF. We were told Vy0 was 0. We know acceleration due to gravity is negative 10. So that tells us that our object was falling for 2.69 seconds. 2.69 seconds. Right, now, how do we use that information? Now we know what our time, we can go back to our big Y equation that we start with, plug it in. We've got to rearrange this, though, so we can find Y0. Pretty simple rearranging. Let's plug in our values. Right? All we did was rearrange this equation here. Solved it for Y0, because we want to figure that's what we're looking for. Plug in our values, because we know YF is 0. We know VY0 is 0. We know our acceleration of 5 meters per second, and we know our delta t, 2.69 seconds. So we're going to square that, put it in. And what does that give us? That gives us an answer of 36.18 meters. So even though these problems have several steps, I want you guys to see that they're not that difficult. We just kind of step through them. And oftentimes there's a step here where we're going to need to find, need to use the fact that we can get some time information right here, YF, right? I'm sorry, we can get some time information from our tan theta equation, or we can get it by looking at how far we fell. There's a couple different ways we can figure out time. So you might have to get a little creative sometimes to find that out, how we're going to get that piece of information. But there's only so many ways you can do it. I think there's two. One way you're going to see you don't have enough information, the other way you do. All right. So that's it for today. Just want to do some more practice on our thetas. I've got an idea tomorrow for something. Hope it's a little bit more fun. I'm just not sure if I can pull it off remotely, but I'll tell you more about that tomorrow. Thanks a lot, guys. Hope this made enough sense. Please take a look at, please don't forget to take the 3-question lecture question quiz today. It'll be pretty simple. I'm not going to ask you so much about doing a calculation. I just want to make sure you're familiar with the process. All right, guys, thanks a lot. We'll talk to you tomorrow. Take care. Bye-bye.